Today we will be continuing with the topic non-aqueous solvents. In the earlier episode, we have discussed what are non-aqueous solvents and how are they different from the aqueous solvents. We have also studied their classification, which included the protic and the aprotic solvents. We also had ionizing and non-ionizing solvents. We have discussed the general characteristics of the non-aqueous solvents, which included their physical and their chemical properties. Apart from this, we have discussed one of the example of non-aqueous solvent, which was liquid ammonia, along with its physical and chemical properties and the reactions which takes place in liquid ammonia. In the end, we discussed the advantages and disadvantages of using liquid ammonia. So, today we will be continuing with the same topic and we will be discussing some more examples of non-aqueous solvents. So, before we proceed with the lecture, let us take a quick look at the lecture plan. The lecture plan goes this way. We will start with the introduction, which we have just now discussed. Then we will discuss one of the non-aqueous solvent, that is liquid SO2. We will discuss its physical properties, solubilities of different substances in liquid SO2, the chemical reactions of liquid SO2. Then we will be discussing another example of non-aqueous solvent, which is liquid hydrogen fluoride. Its physical properties and its chemical reactions will be discussed in this episode. So, let us start with the liquid sulfur dioxide, which is SO2. So, coming on to the characteristics of liquid SO2. It is a non-protic solvent. Non-protic solvent means a solvent which does not contain any hydrogen in its molecular formula. And we can see from the formula that SO2 does not contain any hydrogen, hence it is a non-protic solvent. At room temperature, SO2 is a gas, but it can be easily liquefied by lowering the temperature and increasing the pressure. It has a wide liquid range, that is from minus 10 degrees Celsius to minus 75 degrees Celsius. At a temperature above 10 degrees Celsius, it remains as a gas, because this minus 10 degrees Celsius is its boiling point, and at a temperature below minus 75 degrees Celsius, it remains as a solid, because this is the melting point of liquid SO2. It has low cost and is easy to handle. So, this is one of the advantage of using liquid SO2 as a solvent. It has low dielectric constant, which has a value of 17.4 at minus 10 degrees Celsius. Therefore, it is a good solvent for covalent compound, but a poor solvent for ionic compound, because it has a low dielectric constant. Dielectric constant is inversely proportional to the Coulombic force of attraction between the two ions. Since the dielectric constant is low, that means the force, that is the Coulombic force of attraction between the two ions, is high. Since this force is high, so the ion does not dissociate into the ions, and hence it remains as a non-polar solvent. Therefore, it dissolves the non-polar compounds like covalent compounds. So, these are the physical properties which I have tabulated in the form of a table. Here the freezing point, we can see the freezing point of liquid SO2 is 196.5 Kelvin, the boiling point is 2.63 Kelvin, density is 1.46 gram per ml. This is at minus 10 degrees Celsius, which is its boiling point. The dielectric constant is 17.4 at minus 10 degrees Celsius. Its dipole moment is 1.61 dBi. Its viscosity is 0.428 centipoise and its specific conductance is 4 into 10 to the power minus 8 per ohm per centimeter at minus 10 degrees Celsius. This is the structure of SO2. If we look at the center atom of SO2, which is sulfur, the electronic configuration is written here. It has 6 electrons in its valence orbital, 2 in the s orbital and 4 in the p orbital. Now, one s orbital and 2 p orbital, they get hybridized to form sp2 hybrid orbital. One of the electron which is singly filled, it forms sigma bond with oxygen. So, this red electron we can see, this is the electron which is shared by oxygen. One of the lone pair, it forms coordination bond with oxygen, and one of the lone pair, it remains as a lone pair on sulfur. This remaining electron which is in p orbital, it forms a pi bond with oxygen. So, this is the structure of SO2, and we can say this is the resonance stabilized structure. The bond angle between O, S and O, this bond angle, this is 119.5 degrees and the bond length is 1.43 angstrom. Auto-ionization. SO2 is an ionizing solvent and it undergoes auto-ionization. On auto-ionization, it gives a thionyl ion which is SO2 positive and a sulfite ion which is SO3 2 negative. This auto-ionization takes place in the same way as with water and liquid ammonia. Now, the solubilities of different substances in liquid sulfur dioxide. Amongst the inorganic compound, the iodides and thiocyanates are the most soluble. Then we have metal sulfates, sulfides, oxides, hydroxides which are insoluble. Many of the ammonium, thallium and mercury salts are also soluble. And amongst the organic compound, it is an excellent solvent for covalent compound as we have already discussed, because its dielectric constant is low and hence the force of attraction between the ions is high. Therefore, it dissolves the covalent compounds. Metals are insoluble in liquid SO2. Aromatic hydrocarbons and alkenes are more soluble than aliphatic hydrocarbons. Pyridine, quinoline, ethers, halogen derivatives and acid chlorides are also soluble. Alkanes are insoluble. It dissolves inorganic compounds and behaves as a moderately good conductor for alkali metals and ammonium chlorides, bromides, iodides and thiocyanates. Conductivity of electrolyte solution in liquid sulfur dioxide increases with the size of the cation and it has the following order. Like we can see here, sodium ion, it has a small size, therefore, its conductivity in liquid SO2 is very low. Then we have ammonium ion whose size is greater than that of sodium ion, therefore, its conductivity is little more than that of ammonium. Then we have potassium ion similarly with greater size. Then we have trimethyl sulfur ion and finally, we have tetramethyl ammonium ion whose size is the largest among all these. Hence, the conductivity of this final compound which is tetramethyl ammonium ion, it has the largest conductivity in liquid SO2. The conductivity of anions has the following order. We have thiocyanate, then we have whose conductivity is low, then we have ClO4 minus, we have then chloride ion and iodide ion. So, this is the increasing order of their conductivity. Coming on to the chemical reactions of liquid SO2. The first is acid base reactions. As we have already discussed that liquid SO2 undergoes auto-ionization to gives a thionyl ion and a sulfite ion. Acid are the compounds which increases the concentration of SO2 positive, that is the cation which is called thionyl ion, and bases are the substances which increases the concentration of the sulfite ion which is SO3 2 negative. Neutralization reaction. As we already know that acid plus base gives salt plus water. This is the case if we have a solvent water, but if there is some other solvent like we have some non-aqueous solvent, then this equation becomes acid plus base gives salt plus solvent. So, in this case we have SOCl2, these are the examples. SOCl2, we can see if it dissociate it will give SO2 positive ion, that is the thionyl ion. So, when it dissociate it will give SO2. So, these are some of the neutralization reactions. In this what happens, acid plus base gives salt plus solvent, like in case of water we have acid plus base which gives salt plus water. So, here we have solvent which is other than water. So, whatever solvent we use it is written in the end. So, we can see we have this acid, this is SOCl2 is acid because on dissociation it gives SO2 positive. Since it is increasing the concentration of thionyl ion, it will behave as acid. It reacts with K2SO3, that is potassium sulfite. Now, this potassium sulfite on dissociation will give SO3 2 negative, that is the sulfite ion. Hence, it will behave as base because it is increasing the concentration of the sulfite ion. So, when this acid and base they react together, it will form a salt which is KCl and the solvent SO2. Similarly, we have other examples also. Here we have SOCl2 plus CS2 SO3 which is cesium sulfite. So, again we can see that SOCl2 is an acid and this cesium sulfite is a base. So, when this acid and base it reacts, it forms cesium chloride which is the salt and the solvent SO2. Similarly, we have thionyl bromide plus tetramethyl ammonium sulphite. Again, SOBr2 is a acid and this containing SO3 is a base. So, when these two acid base react, it will form a salt and a solvent SO2. Similarly, the last example, we have thionyl isocyanate. It reacts with potassium sulphite, this is the base, and thionyl isocyanate is the acid. It will form a salt which is potassium thiocyanate and the solvent SO2. So, we can see in all these reactions the acid and base, they react together to form the salt and solvent, hence these are the neutralization reactions. Compounds of zinc second and aluminum third shows amphoteric behavior in SO2. Amphoteric behavior means that a particular compound, it can behave as an acid as well as a base. So, we can see here are some examples which shows the acidic and basic character of zinc second and aluminum third compound. So, in the first example, we have zinc chloride, that is zinc is in +2 state, it reacts with potassium sulphite to form salt and ZnSO3. In the second example, we have aluminum chloride plus potassium sulphite, it forms KCl plus aluminum sulphite. So, these two reactions, these shows the acidic nature of zinc second and aluminum third respectively. Now, coming on to the next example, which will show the basic character of the same ions, that is the zinc second and aluminum third. Here we have zinc sulphite, it reacts with potassium sulphite to form a salt. Then we have aluminum sulphite plus potassium sulphite, again these two react to form a salt. So, these two examples, these shows the basic character. So, we can see that the compound zinc 2 and aluminum 3, these shows both type of character, that is acidic as well as basic, hence these have amphoteric nature. The second is the solvolytic reactions or solvolysis. Solvolysis is basically what happens when the solvent it breaks into ions, then one of the ion or even both the ions, they can react with the solute to form the compound. So, here we have only limited number of salts undergo solvolysis in liquid SO2 and ammonium acetate is solvolized in SO2 as follows. So, this is an example we can see here, we have ammonium acetate, it reacts with SO2 to form ammonium sulphite plus thionyl acetate. So, we can see that this SO2 on auto-ionization, this gives sulphite ion and thionyl ion, and this sulphite ion and thionyl ion, these react with the solute molecule to form the to give the solvolysis reactions. Now, second we have thionyl acetate, it undergoes solvolysis to give SO2 plus CH3CO whole twice O. This is an anhydride. Some covalent halides also undergo solvolysis in liquid SO2. Like we have some examples here, PCl5 plus SO2, it gives POCl3 plus SOCl2. Arsenic pentachloride plus SO2 gives arsenic OCl3 plus SOCl2. Then we have uranium hexachloride plus SO2, it will give UO2Cl2 plus SOCl2. Then we have tungsten chloride, it will react with SO2 to give WOCl4 plus SOCl2. Solvation. Solvation is basically what happens, the solvent molecule, it surrounds the solute molecule to form the addition compound. These are called solvates. Like in case of water, we have hydrates. So, this liquid SO2, it also forms solvates. So, the formation of solvates, that is addition compound, takes place as follows. We have sodium iodide, an example here, it reacts with SO2, which is the solvent molecule. So, here the addition compound is formed, which is NaI.4SO2. Similarly, with potassium iodide, it forms Ki.4SO2. Next are the precipitation reactions. Precipitation of a compound depends upon its solubility. A large number of precipitation reactions can be carried out in liquid SO2 due to specific solubility relationship. We have barium iodide and zinc thiocyanate, it forms barium thiocyanate, precipitate of barium thiocyanate plus zinc iodide. Similarly, we have lead fluoride plus lithium sulphate, it will form a precipitate of lead sulphate. The compound which is less soluble, it gets deposited as a residue and it is called the precipitate. Next we have antimony chloride plus lithium iodide. So, it will give antimony iodide precipitate and in addition it will give lithium chloride. Thionyl chloride in liquid SO2 is used to prepare many compounds, like we have silver acetate. It reacts with thionyl chloride to form a precipitate of silver chloride plus thionyl acetate. So, silver chloride can be prepared by this reaction. Similarly, we have ammonium thiocyanate. It reacts with thionyl chloride to form a precipitate of ammonium chloride plus thionyl isocyanate. So, again ammonium chloride can be formed by this reaction. This can be removed by filtration. Next, we have potassium iodide, which reacts with thionyl chloride to form a precipitate of KCl, that is potassium chloride, which can be removed from the solution. Since it is a precipitate, on simple filtration it can be removed. Next, we have complex formation reactions. SO2 does not itself take part in complexation, but it serves as a medium for complex formation. The solubility of iodine in liquid SO2 is greatly increased by the addition of potassium and rubidium. This is due to the formation of the complex Ki3 and rubidium iodide. So, this iodine is not soluble in liquid SO2, but if we add Ki, it forms Ki3. Similarly, we can add rubidium iodide also, it forms RbI3, and this Ki3 and RbI3, these are easily soluble in liquid SO2. So, it enhances the solubility of iodine in liquid SO2. When HgI2 or cadmium iodide is dissolved in liquid SO2 in presence of Ki, the solubility of these iodide is increased due to the formation of a soluble complex K2Mi4. So, here we have Mi2, which is metal iodide. The metal can be mercury or cadmium. So, if we add Ki, the solubility of this metal iodide increases and it forms a complex K2Mi4. So, due to the formation of this particular complex, the solubility increases. When solutions of salt like aluminum chloride or zinc chloride in liquid SO2 react with excess of a compound containing sulphite ions, soluble sulphito complexes are formed. So, this is aluminum chloride. When it reacts with potassium sulphite, this is a soluble complex which is formed here. Similarly, when zinc chloride it reacts with potassium sulphite, again a soluble complex is formed. This is potassium zinc sulphite complex and in addition KCl is formed here. Hexahalo complexes, that means a complex which contains 6 halogen atoms in liquid SO2 are formed by the action of covalent halides like SbCl3 or SbCl5 on alkali metals. So, we have some examples here. This is SbCl5 plus NoCl. So, what will happen? NoSbCl6 is formed. So, hexahalo complex is formed here. Similarly, we have other examples when SbCl3 reacts with 3 molecules of KCl, so K3 SbCl6 is formed. Similarly, other examples also we can see this one. This is SbCl5 plus tetramethyl ammonium chloride. So, here what happens? This is tetramethyl ammonium and this is hexachloro antimony. So, this particular complex is formed. Next is the redox reactions. Gaseous SO2 is known to behave as both oxidizing and reducing agents. Liquid SO2 does not have any strong oxidizing or reducing property, but it serves only as a medium for redox reaction. And we are not interested in gaseous SO2 because we are talking about solvent, we are interested in liquid SO2. So, liquid SO2 cannot reduce iodine, however, a sulphite in liquid SO2 reduces iodine to iodide. So, we can see in this example we have iodine. When it reacts with any sulphite, it changes to iodide. We have Ri here. So, in the reactant form we have I2 whose oxidation state is 0. Here the oxidation state of iodine is 0, while in the product form, that is Ri, here iodine is present in the form of iodide with the oxidation state of -1. So, the oxidation state has decreased and this iodine has been reduced to iodide. Ki is oxidized to free iodine by FeCl3 or SbCl5 in liquid SO2. So, in this example we can see Ki when it reacts with SbCl5 or FeCl3, it changes to free iodine. So, here the oxidation state of iodine is -1 and in the product it is 0. So, we can see the oxidation state has increased from -1 to 0 and it has been oxidized. Organic reactions in liquid SO2. SO2 serves as one of the best medium for the reactions where inert and non-inflammable solvent is required. For example, we have sulfonation. In liquid SO2 medium, a good yield is obtained. So, this is benzene when it reacts with chlorosulfonic acid in a medium of liquid SO2, it forms benzene sulfonic acid. Bromination, the second reaction is bromination. Liquid SO2 is used for both addition and substitution reaction with bromine. So, this is styrene when it reacts with bromine in liquid SO2, this bromine gets added to the double bond. So, we have dibromo complex here. Next is phenol. When phenol is reacted with bromine in liquid SO2, a para-bromophenol is obtained. Since this OH group is ortho-para-directing, so the major compound obtained here is the para-bromophenol. So, these all reaction can take place easily in liquid SO2. Next we have Friedel-Crafts reaction. AlCl3 is highly soluble in liquid SO2 and therefore preferred over ether, which is highly inflammable. So, this Friedel-Crafts reaction can be easily carried out in liquid SO2. When benzene reacts with benzoyl chloride, we have benzophenone as a product. Coming on to the uses of liquid SO2. It is a solvent of intermediate dielectric constant. Certain compounds are soluble in it and some are insoluble. It is a useful solvent for several types of synthetic reactions and in refining of certain types of petroleum products. The next example we will be discussing is liquid hydrogen fluoride, which is HF. So, coming on to its general properties, it is a water-like non-aqueous solvent. It is water-like because on dissociation it gives H ion, like water gives H ion. So, but it is a non-aqueous solvent. It is a protic solvent, as can be seen from its molecular formula, which is HF. It contains a hydrogen in its molecular formula, hence it is a protic solvent. It is also an ionizing solvent and it undergoes auto-ionization to give H2F positive, which is fluoronium ion, plus F minus, which is fluoride ion. Next is the physical properties of liquid HF. So, the physical properties have been tabulated in the form of a table. The freezing point of liquid HF is -83 degrees Celsius. Its boiling point is 19.4 degrees Celsius. The dielectric constant is 84 at 273 Kelvin. Dipole moment is 1.9. Specific conductance of liquid HF is 1 into 10 to the power -6 per ohm per centimeter. This is at 263 Kelvin. So, it has a wide liquid range as we have already seen from the table. We can just go back. Its freezing point is -83 degrees Celsius and its boiling point is 19.4 degrees Celsius. So, it remains liquid between these two temperatures. At a temperature above 19.4 degrees Celsius, it remains as a gas, and at a temperature below -83 degrees Celsius, it remains as a solid. Next is it has high dielectric constant, which we have seen from the table, whose value is 84. Since it has high dielectric constant and we already know that the force of the Coulombic force of attraction between two ions is inversely proportional to the dielectric constant. Since the dielectric constant is large, the Coulombic force of attraction between the ions would be low. Since the value is low, the solvent, it can be easily dissociated into ions. So, now the solvent is a polar solvent. So, it will dissolve the polar or ionic compounds. So, it is a good solvent for ionic compounds. It has low specific conductivity, but high dielectric constant make it an excellent ionizing solvent. The solubility of compounds in liquid hydrogen fluoride. Inorganic compounds are more soluble than the organic compounds, because we have already seen it is a polar solvent, so it will dissolve the polar compounds. Dissolution of solutes in liquid HF can undergo any of the following mechanism. Dissolution by normal dissociation into ions. It dissociates in the same manner as other ionizing solvent, like for example water or liquid ammonia. So, here we have the example hydrogen fluoride HF, it dissociates to give H positive plus F minus. So, we have SbF5 here. When it reacts with HF, what happens? It will take the fluoride ion and it will form SbF6 minus plus H positive. Similarly, PF5, when it reacts with HF, it will form PF6 minus plus the proton. So, we can see that it is giving a proton here, so it will behave as an acid. So, such solutions are acidic in nature. Chemical reactions of hydrogen fluoride to the solute followed by its dissociation to give fluoride ion. This is the acetic acid. When it reacts with HF, it forms CH3COOH2 positive plus F minus. So, we can see here that acetic acid, which is acid in water, it behaves as a base here, because instead of giving a proton, it has accepted a proton. So, it is a base and HF is a acid. Similarly, we have HNO3 plus HF. HNO3 is also not giving a proton, but it is accepting a proton, hence it also behaves as a base in comparison to the HF. KNO3 plus HF, it will give H2NO3 positive plus 2 fluoride ion. So, we can see all these behaves as these acids, these behave as base in front of HF. So, HF is a very strong acid. The anion of the solute may be replaced by fluoride ion. So, we have KCN and HF, their anions get interchanged. So, now we have KF plus HCN, similarly Ki plus HF, the anions, on interchanging the anions we have Kf plus Hi. Chemical reactions involving more than simple replacement may take place. We have sulfuric acid H2SO4 plus HF, it will give HSO3F plus H2O. So, here simple replacement of ions have taken place. We have water plus HF, so it will give H3O positive plus F minus. Chemical reactions involving more than simple replacement may also take place, like we have sulfuric acid plus HF. So, these two combine together to form HSO3F plus water, and water plus HF, these combine to form the hydronium ion and the fluoride ion. Auto-ionization of liquid HF, this I have already discussed. It forms a fluoronium ion which is H2F positive plus a fluoride ion which is F minus. Coming on to the chemical reactions of liquid HF. The first one is the acid base reactions. Auto-ionization of liquid HF is similar to that of water, but its behavior is different because it is a strong proton donor and is able to donate proton even to those compounds which are able to attract proton from water. We have seen few examples just now. So, the compounds which behave as acid in water, they behave as a base in front of this HF. There are many compounds which acts as acid in water, but as a base in liquid hydrogen fluoride. For example, we have here HF plus HF, it will give, this is simple auto-ionization reaction, a fluoronium ion and a fluoride ion. Then we have ROH, this is alcohol plus HF, it will give, so this alcohol will accept a proton from HF and it will give ROH twice positive plus the fluoride ion. Next we have acetic acid, which is again an acid in water, but in HF it accepts proton to form CH3COOH2 positive plus a fluoride ion. KNO3, again it reacts with HF and it behaves as a base and form NO OH whole twice positive plus potassium ion and the fluoride ion. HClO4 is considered to be the strongest acid in aqueous medium, but it shows the amphoteric nature in liquid HF. Amphoteric, like I have discussed it earlier also, that means it can behave, a particular acid or a particular base can behave as an acid or a base. HClO4 is considered to be one of the strongest acid in aqueous medium, but it is amphoteric in liquid HF. Amphoteric nature means that a particular substance can behave as a acid as well as a base. So, we have HClO4, when it reacts with HF, it can form H2ClO4 positive. That means it has accepted a proton from HF. So, here it is behaving as a base in the first equation. In the second case, HClO4, when it reacts with HF, it is donating its proton and it forms ClO4 negative plus H2F positive. So, in this case it is behaving as a acid. So, we can see that HClO4 can donate its proton as well as it can take a proton. So, it can behave as both acid and base, and hence it has an amphoteric nature. The only compounds acting as acid in liquid HF are some electron acceptor fluorides. Example, BF3, ASF3, PF5 and SBF5. So, all these are electron acceptor fluorides and these behave as acids in liquid HF. These are the, here we have the equations. BF3, when it reacts with HF, it forms H2F positive plus BF4 minus. So, it is furnishing H2F positive, that is a fluoronium ion, hence it behaves as a acid. Similarly, SBF5, when it reacts with HF, it forms again a fluoronium ion and SBF6 minus, hence it is a this SBF5 is an acid. These acceptor molecules dissolve in HF to give solutions which dissolve electropositive metal like magnesium, which is also an evidence in favor of the acidic nature of solutes. Ionic fluorides acts as base in liquid HF and increases the concentration of fluoride ions. Next is the precipitation reactions. Only few anions like we have ClO4 minus, BF4 minus, HF2 minus, these are stable in liquid hydrogen fluoride. So, we have this is sodium sulphate, it reacts with silver fluoride to form Ag2SO4 precipitate plus NaF. Next we have NaClO4, it reacts with AgF to form AgClO4 precipitate plus NaF. Next barium ClO4 whole twice plus 2AgF, it will form a precipitate of AgClO4 plus BaF2. Gases like HCl, HBr, Hi when passed through AgF or TLF in liquid hydrogen fluoride, corresponding silver or thallium halides are precipitated. As we have here HX plus AgF in this in liquid HF, what happens, a precipitate of AgX is formed, and when this HX, this can be HCl or HBr or Hi, when it reacts with thallium fluoride in liquid HF, a precipitate of TLX will be formed. We have another reaction where we have AgNO3 plus BF3, when it reacts with liquid hydrogen fluoride, we have a precipitate of silver borofluoride. Next are the solvation reactions. Solvation reactions again are the addition compounds which are formed when the solvent molecule it surrounds the solute molecule. Like in case of water we have hydrates, similarly in case of HF we have solvates. Example, we have KF.2HF, ammonium fluoride .HF, this is diethyl ether .2HF, ethanol .HF. So, this .HF means this is the solvate molecule which is surrounding the solute. Redox reactions. These reactions are similar to those of metal with HNO3 in aqueous medium. We have silver plus nitric acid which forms silver nitrate plus NO plus water. Silver with HAsF6, it forms silver AsF6 plus AsF3 plus hydrogen fluoride, and silver with HIF6, it forms AgIF6 plus Hi plus 6HF. Reaction with organic compounds. Many organic compounds like alcohol, phenol, ether, aldehydes, ketones, acids and acid anhydrides etc., they dissolve in liquid hydrogen fluoride to give solution of high conductance. This is due to the formation of ions, which can be explained as follows. We have alcohol ROH plus HF. So, this HF, it will furnish a proton to the alcohol and it will form ROH2 positive plus HF2 minus. Similarly, we have this is ether, it reacts with HF to form R2OH positive plus HF2 minus. Next we have R2CO, which is any carbonyl group, it can be aldehyde or a ketone. When it reacts with HF, it forms R2COH positive plus HF2 negative. Similarly, anhydride, when it reacts with HF, it will take a proton from hydrogen fluoride and form RCO whole twice OH positive plus HF2 minus. So, we can see that in the product we have ions which are cations as well as anions, and due to the presence of these ions, it has a high conductance. Reactions with inorganic compounds. A number of inorganic compounds such as alkali metal sulfates, iodates, periodates and perchlorates dissolve in liquid hydrogen fluoride. Like in this reaction we have MF5, where M can be any metal, like it is not exactly metal, it can be non-metal also, like we have phosphorus, arsenic or antimony. When it reacts with HF, it will form MF6 minus plus H positive. Reaction with inorganic compounds, we are continuing with this. Certain simple salts are solvolized in liquid HF, like we have KCl. When it reacts with HF, it forms K positive plus F minus plus HCl. Similarly, we have KCN plus HF, it will form K positive plus F minus and HCN. Solvolysis reaction occurring with KNO3, K2SO4 etc. are followed by secondary reactions. We have KNO3 plus HF, it will form HNO3 plus K positive F minus. Now, this HNO3 which was formed in the as a product in the earlier reaction, it again react with HF to form H2NO3 positive plus a fluoride ion. Now, this H2NO3 positive formed as a product in the second reaction, it reacts with hydrogen fluoride to give a protonium ion plus NO2 positive plus a fluoride ion. Similar type of reaction takes place with K2SO4. So, K2SO4 reacts with hydrogen fluoride to form H2SO4 plus KF. Now, this H2SO4, it again reacts with HF to form HSO3F plus water, and the water reacts with HF to form this is a protonium ion plus a fluoride ion. So, this was all about the two solvents which we have discussed, that is liquid SO2 and hydrogen fluoride. Coming on to the summaries of today's lecture. Today we have discussed the physical properties of liquid SO2, the solubilities of various substances in liquid SO2, chemical reactions taking place in liquid SO2. Then we have discussed another solvent which is liquid hydrogen fluoride. We have discussed its physical properties and chemical reactions. So, this was about today's lecture. But the topic has not finished yet. In the upcoming lecture, we will be discussing one more example of non-aqueous solvent, which is N2O4, that is dinitrogen tetraoxide, and apart from this, we will also be discussing the molten salts.